So for any induction proof, we essentially have two steps based on those things that we saw in the last couple of videos. First, we have to show that the base case is true, where usually that's S1. And that means plugging in n equals 1 there and seeing that we get a statement that holds. We don't necessarily have to make the base case 1. There are some cases where having it be 2 or 0 or any other number fits for whatever specific reason, but just for the sake of simplicity and the fact that it's most of what we're going to be looking at here, we'll say that that base case is generally showing that S1 happens, or at least that it should. And then from there, we have to show that if Sk is true, then that implies Sk plus 1 is true. And that's where most of the work is. But essentially thinking back to the staircase, this is saying, can we get on? And if I can be at one place, can I go to the next? Where this notation, it's not the most instructive in and of itself. To really understand an induction proof, you have to prove things, which we'll see. So for our first example, we want to use mathematical induction to prove that the following statement is true, where the statement is that one we made earlier about the sum of natural numbers. That is, the sum of the first n of them, 1 up to n, is n times n plus 1 over 2. Now before I get into this in detail, you know that this one actually is true, because I talked about it earlier on with that sort of Gaussian counting argument of grouping things at the ends and working towards the middle to get that pattern. Often, if you go far with math, you'll see that there isn't necessarily just the one way to make an argument. Especially with things like this, there's usually options for counting your way through something, or there's some cleverness you can use with formulas, or, well, you can use something like this. Use something like induction to argue that the pattern will hold. Where, when we're doing these types of things, technically, we like to be clear that we are going to be making a proof. We like to let the world know that we're trying to show something specific. And if we want to show something specific using induction, we have to start by showing the base case, S1 holds. And I'm going to be a little bit more thorough with my notation than I usually am here, because proofs are kind of built around thoroughness and specificity. You really want to leave no doubt that what you're doing is not only correct, but appropriate. The ideal proof, it says exactly what it needs to. And we'll see what sort of thing we can get here. I'm going to be a little more detailed than maybe a technical proof from the book would be, because it's our first one. But just know that we're trying to be as exacting as possible in our language here, because we want this to be as clear and obviously true as we can possibly make it. So if we're showing S1 holds, well, we need to say what S1 is, where in this case, S1, as we saw earlier, is the statement that the first 1 natural numbers added up is equal to 1 times 1 plus 1 over 2, which here is just 1. And as I said earlier, usually S1 is like a half step above being given. It's kind of obvious so long as you understand what the notation is, but we still technically need to be sure. Very, very rarely are there going to be cases where the base doesn't work, but the inductive step does. So even so, we just have to be sure that we can actually get on the staircase as a part. But here, this 1 equals 1 is obviously true, so the base case holds. And for our inductive step, what we have to do is first assume that Sk holds. That is, assume we have that the sum of the first k natural numbers has form k times k plus 1 over 2. And it might seem like we're just getting this kind of for free, but this is sort of what the base case implies, is that we can start somewhere. And as a result, we can generalize that out to say something about our kth term. And once we have our kth term, what we want to do is take that and twist it around to get what happens at the next term. Where at the next term, We have all of those same things as we got in the k term, but now we're going up to k plus 1, which means that this guy changes just a little bit, as we saw in that last video. And our goal here is going to be to recognize that things we have in here appear as well up there, and see if there are ways that we can put together the things that we have up here and down there to get towards a obviously true statement. Where the first thing we can do is, well, if we think about this k plus 1 term, and we group this first set of things up to k, that's what we have up here. So what we're going to do is we're going to take all of these pieces and replace them with that thing that we are assuming is true. So we're going to take this and return it into k times k plus 1 over 2 plus k plus 1 equals that thing that we're trying to prove, that thing that we don't know for sure, but we're going to hopefully be able to make an argument for. And actually, we're pretty close. It's just a couple more steps away to be able to get to something that is perhaps not obvious, but, well, we'll see that it makes sense. So what I'm going to do here is combine a couple of steps. I'm going to multiply in that k, and over here I'm going to find a common denominator, squeeze these together because I'm running a little bit low on space, but hopefully we'll still have just enough. So if I multiply these in together, I'll get k squared plus k, and then to get that common denominator with a 2, I'll multiply a 2 in over there to get 2k plus 2, and that's all over 2, which this we're still hoping is going to be equal to that. You know, we're throwing these equalities in here with the idea that it's going to work. We don't know for sure just yet, but if we look at what we have here, we can bring in that k, and if we bring in that k with the 2k, we get k squared plus 3k plus 2, which, not coincidentally, is equal to k plus 1 times k plus 2 over 2, which is exactly what we were hoping to get. That is, with a little bit of rearrangement and one replacement based on what we assumed held, we went from a statement that is not obvious to one that is about as clear as any mathematical statement could ever be, that thing equals thing. In this case, it's k plus 1 times k plus 2 over 2 equals k plus 1 times k plus 1 over k plus 2 over 2. But that's the idea, is you take your step here, make some sort of adjustment, pull it in there, push the algebra around a little bit, and you should end up with something that is about as clear as it ever gets. Where the hardest part with these proofs is, for one, getting your head around the notation, and then two, being able to see this kind of connection reasonably quickly. It's not obvious all the time. In this case, it's, I wouldn't say as nice as it gets, but it wasn't too terrible. Sometimes it's a little more subtle, sometimes it takes more manipulation, but this is always the process that we're going to follow, where once we have this obviously true thing, we would say something to the effect of, thus, the inductive step holds, and by the process of mathematical induction, we have shown that the statement is true. Where, you know, I ran out of space, so otherwise my notation would be a little bit nicer, but at the very end of a proof, you always write some little symbol that says, hey, we did it. Some places it's a QED or an upside down triangle of dots, and in some places you draw a box. But you always want to make sure that people know you're starting by trying to prove something, and hey look, you did your job. Anyway, this is one example of how you can use induction. Next we're going to see another in the context of De Moivre's theorem, as promised about a month ago.